Okay, so what we're going to do today are two things. Well, 2.01 things. One is that there's yet another way to make a a zero tuple in Python that Jason Grau pointed out, which is that you can simply write open close parentheses in Python, and that will give you a tuple. So that gives you the zero tuple. So right here, I type open close parentheses, and the output is the zero tuple. So just a remark that there's yet another way of doing that. Zoom in a little so you can see this. Okay. I guess the syntax highlighting around parentheses makes it hard to see that. So that is a way to make a zero tuple. Not very exciting, but you can do that. Okay, so the next thing we'll talk about is ways to use Sage. We'll go over a couple of ways of doing that, and then we're going, and also Cython. Maybe I should write Cython because these each support using Cython. And then we're going to start talking about Cython. Before we get into all this, are there any questions? I bet there's a question. So, are there any questions? I refuse to give this lecture unless somebody asks me a question before I start. Come up with something about this class.
Why does it take 2 hours to build Sage from source?
Because it's 6 million lines of code.
Can you parallelize the build process?
Yes. There's something called the Sage Installation Guide. You go to sagemath.org. It's under documentation. And then if you look for installation guide, there's a whole bunch of environment variables. Install from source, environment variables. So they're all documented here. And in particular, you can have fine control over various parallelization aspects of the build. The sorts of things that you might parallelize in building Sage are as follows. One, there's about 100 packages that get built in the course of building Sage. You could hopefully build them all at once. Of course, that doesn't make any sense because some of them depend on other ones. For example, the arbitrary precision integer arithmetic, it doesn't really depend on much of anything, but say the integer matrix library, that depends on the arbitrary precision integer arithmetic. Or Peri, the sort of number theory library, depends on arbitrary precision arithmetic. Or the numerical linear algebra code for Python, NumPy, that depends on the numerical linear algebra library. So there are lots of dependencies, but fortunately you can build in parallel at least as much as is allowed by those dependencies. And to do that, I think, let's see, you set there's an environment variable called make, all caps, and you just set that. Somewhere it should be documented in here. To make -j num. And that will, so if you do, right before you build Sage, if you type export and then make equals, in quotes, make -j20, then it will, let's see, what will that do exactly? I'm not even sure what it does these days, but I think what it does is that when it tries to build, wow, so it's complicated. I don't know what the latest is, but I know that if you type this, when it tries to build individual packages, when it uses the make command in each individual package, it will then instead use this command. And so for individual packages, it will, in many cases, when possible, build using 20 processes at once. So individual packages will build more quickly. But it also, I think, has an impact on how many different packages will build at the same time in parallel. So, so you can read it. It's changed. I mean, when I wrote it first, this just influenced how individual packages built, how many at once. And I think when I made it so that multiple packages would build in parallel, I think I just used the same number. So it would do 20 in parallel, and each one it would do 20, which is kind of silly, and I'm sure that somebody has modified it since then. So probably Sage num threads allows you to fine-tune what the various parameters are. But anyways, look at this particular guide. There's a lot of things you can control in the build process. For example, so the numerical linear algebra library is called Atlas. This is what takes most of the time when building Sage. It stands for Automatically Tuned Linear Algebra Software. It's a complicated program basically for multiplying two matrices with floating point entries. And what it does is it does a kind of optimization problem where it tries lots of different parameters to figure out what on your computer are the best parameters for multiplying matrices of various sizes. And this takes a while. But many machines, like if you install Linux on your machine, you probably can just do apt-get install and then Atlas, or at least some variant of Atlas, and then, I mean, that's if you're using Ubuntu, but if you're using, Red Hat, you might do it some other way. But you can install a system-wide Atlas library, and then there's a flag or a variable that you set here, which allows you to tell Sage to use that system-wide Atlas instead of building it itself. That said, you may get worse performance than what you get by building it yourself. Typically, if you take a generic numerical linear algebra library and just try to drop it on your system, you can easily see a factor of 2 or 3 or even 4 in performance difference over what you can get by custom building yourself and just waiting for Atlas to build. On the other hand, it can build a lot more quickly. For example, I was building Sage on I have a little Chromebook, one of those Samsung $250 ARM Chromebooks, and I built Sage on it. And when I tried to have it build Atlas, it just sat there for seemingly days, and I gave up. So then I just used the Atlas that's in Ubuntu for that machine, and it worked very quickly to build Sage. But you can, on a machine with a lot of cores, you can build Sage in like a half hour. If you have a fast hard drive and a lot of cores. If you have a really slow hard drive, it will take an enormous amount of time. If you try to build it on Cygwin under Windows, where the disk access is really, really slow, and every time a fork occurs in a process, so in Cygwin, forking is extremely expensive, and it happens a lot in standard build systems that are designed for a Unix-type environment. So it can easily take days to build Sage in Cygwin, in my experience. So that's kind of painful. Okay, so that answers your question. But do look at the installation guide, which I just scrolled by in front of you. All right, so build Sage from source. Also, one remark about the value of building Sage from source is that Sage includes almost all of its dependencies. So what you do is you get the Sage tarball. It's a single file. You download it, you extract it, and you type 4 letters, make. And it will go off and it builds about 100 different things self-contained in that directory where you extracted the tarball, puts it all together, and then gives you the result. It doesn't affect anything else on your system, completely unrelated. It'll use very little that's also on your system. You need some sort of compiler to get things going, but if you have a known to be very buggy version of some compiler, then it will build its own compiler. So for example, the GNU compiler collection, GCC, is part of that tarball you get when you get Sage. And on some systems, it builds GCC in order to avoid issues with buggy compilers. What you run into with math software, it's kind of different than like with a graphic, like Photoshop or something. I mean, who cares if some pixel is slightly off in when you're manipulating an image? But with math, what will happen is the very slightest error in the compiler, turning some code into something else that it thinks will be just as good or just as correct and faster, can result in in fact, will almost always result in completely wrong answers. And our test suites pick that up, hopefully. And so we discover a lot of compiler bugs and other issues in the course of building and testing Sage. And then we flag them. Okay. All right, so that's building Sage. And if you want to do it, you just go to sagemath.org, and right there, there's a link to the source. So you click there, you choose a mirror, download the source tarball, extract it by double-clicking on it, and then you have to use the terminal in OS X, and you go into that directory and type make. Or you can also get it from BitTorrent or whatever. Okay, so that's that. All right, the next thing I want to talk about is some ways to use Python, and I'll point out at least 3 that are all web-based. Of course, you can also use Python by installing Python and Python on your computer and building there, or just installing Sage and building there. So I think if you install Python in any way, then you can easy install, or there's like 4 different Python package managers, and they should all have Python. If you're using Linux, you can do whatever your standard package manager is, you can get Python that way, like apt-get install Python. Okay, so first there's one thing is the Sage Notebook server. I have one that's kind of aimed at this course called SageNB, called 480.sagenb.org, which I've typically used in the past specifically for this course. So you can go to this website, for example. Although the machine this runs on can get heavily loaded, so there's a lot of people like using it. You go here, there's no place to create an account, and I think signing in with username and password doesn't really make sense because there's no way to make an account. But what you can do is you can click on menus like Google, Yahoo, etc., and it'll just say signed in. So you can use this OpenID. We used to have account creation, but basically what happens is people create accounts and then they forget their passwords. And we hadn't implemented password reset, and so it just got really ugly really quickly. So just disable the account creation. So if you just go to this website, click on whatever your favorite OpenID provider is that you have an account with, then it should just very quickly log you in. Maybe I'll make a brand new account associated to my email for this course. And I say allow, and there it is. This works, something's wrong. Error username already is, that seems reasonable. Wstein 480. Okay, and now I'm in. Here it is. This notebook, the main advantage to this probably is that it's, so, I mean, me and this guy, Alex Clemishaw, started writing this in 2006, a long time ago. And so it's pretty stable and debugged. It's really just been polished up a lot over the years and improved. Of course, it still has it basically looks like Google Docs used to look in 2006. Almost exactly like Google Docs looked in 2006. So it has a very 2006-ish look. In any case, try out Python. But here it is. You have a little worksheet. You can type code like 2 plus 3. Wow, and we're out of disk space. As I said, there's a lot of people that use this server, and so you can run into issues. That's pretty ugly. Apparently the collective users have used up the hard drive, maybe the temp directory, and so we're not going to get anywhere. So much for that. And now I have to remember to fix that as soon as class is over. Dang. Yeah. Okay, so much for that. You probably don't want to use that. So the next thing to show you is sagecell.sagemath.org. And we've recently, at the last Sage Days that I went to, we did a lot of work to make this more, basically make this more highly available by I'll explain that in a second. So this is a nice site because it's incredibly simple. All it is you go to this site and you get a box in which you can type Sage code, which, or there's a little language drop down, which unfortunately doesn't have Python. I complained about that, and it should get added soon. It has various languages like R, Python, Octave, and Sage, and so on. You type in code, and you evaluate it. And it's just one single thing. That's why it's called the cell. You get one input and one output. The sorts of things you can do that are pretty sophisticated. Like, it's no problem to say, draw a 3D. Actually, I have no idea if this will work given how people. Whoops, screws are obviously 3D. Yeah, this uses Java, and nobody likes Java these days. But, yeah, I remember every time you upgrade OS 10 these days, it says security enhancement. We have disabled Java. So let's see. I'm not going to show you a sphere. I will do I'll do plot sign. So just like, oops, So there's a plot of sine in a second. That's pretty crappy turnaround time for computing a plot. Very unimpressive. Well, I don't know if that's going to take forever, but let's see. How about, well, that's pretty terrible. In any case, that's pretty interesting. What happens is you do a calculation. You can get a link to the calculation, which is nice. You just get this URL at the top. You can copy and paste this and then give it to somebody, and if somebody else goes to that website, they'll see the cell with that code in it, even if it's a lot of code, like a couple of pages of code. So it can be a really easy way of sharing a snippet of code that does something. Although this one's pretty useless. Oh, okay. So there's a plot of sine from, let me make it more interesting. I guess the problem was that it was sort of spinning from me messing it up before. So you can draw little plots, and in fact you can do anything you do in Sage, so it's pretty sophisticated. One problem is that there's no little language equals Python here. So if you want to evaluate Python code, you have to do Python and then give it as a big string like this, I think. And of course I haven't told you anything about Python, but this is a very small example of Python code. I think this should maybe define a function in Python. Yeah, that was pretty boring. It'll square a number. So what this did was it turned that little two-line function into some C code, compiled the C code into a shared object library, linked that library into the running Python process, and then it made a function f available, which is then called. So that's a really little example of using Python from this website. And the cool thing again is that you can, for example, click on shortened temporary link, and you get this link, and then you could just paste that into an email and then send it to somebody. And when they go to that website, they should see the same thing. So it stores the code in a database. Yes, it has. I don't know what the current timeout is, probably about a minute or something. Also, here's an example. Let's see. Puget Sound. So the really neat thing is you can embed these little cells in any web page anywhere. So here's an example of a page at University of Puget Sound down south from us. So it just looks like a normal web page, but look at that. This is literally, it's exactly the Sage cell server we were just looking at. There's a little bit of extra code you can paste into a website and get that embedded in your web page with some code typed in already. And so if you just click this, it evaluates the code and then displays it. And again, this is in any, like if you have a website somewhere and you just want to stick a little bit of Sage in it as an example, you can do this. You don't have to install anything at all. You just put a little code in your website. And what it does behind the scenes is it contacts the server and does the calculation. The server, by the way, for a while it was just one computer, the same computer running the main Sage Notebook server running in Padelford. But now what we have is a separate new machine in Padelford for this, plus in addition, a machine across campus in the UW Tower. So we have multiple locations, which is good. So as long as either one of them is working, then this will work. And the user who goes to your website can just change stuff if they want. So for example, I guess if I do that, and it gives me 30 factorial, but you can change the number and get a different output. All right? So that's, yeah, it's working nice and snappily. You should be able to compute pretty large factorials pretty instantly. You might wonder, how long does it take to compute a large factorial? Nope. It uses a good algorithm. N, 10 to the power 5, 100,000 factorial. I don't want to print out the answer because that would take a long time. That takes 0.04 seconds. 10 to the 6, a million factorial. Takes 0.62 seconds. How does it do that? It definitely does not do 1 times 2 times 3 times 4 times 5. Yes? No. But so the basic idea is if you were to do 1 times, this is just the basic idea and it gets you really close to the speed but doesn't quite do it. If you want to compute n factorial efficiently, and this is really computing every single digit of n factorial, not just a little bit, and it does it pretty dang fast. The idea is the following. So the naive approach, which is 1 times 2 times 3 times 4, that involves doing n minus 1 multiplies. And by the way, you definitely don't want to do that recursively when you stack them. So if you do that, that's n minus 1 multiplies. I'll tell you a different approach that involves even more multiplies, but it's actually dramatically faster. So 1 times 2 times, directly that's, if you do that, it's 1 multiply, so that's n minus 1 multiplies. These are horrible, bad multiplies, because each time you're multiplying a humongous number times a little tiny number, right? Like the very last one is 1 times 2 all the way up to n minus 1. That's a huge number, really, really big, times n. So that's a big number times a small number. That's bad. Up. So it turns out that when you work really hard to try to understand how to multiply numbers well, if you have two numbers of roughly the same size, you can like say both have I don't know, 1 million digits. You multiply those two together, there's a certain amount of time it takes, but it's not much different than the time it takes to multiply a very small number times a million digit number. So basically, the size of the biggest number when you multiply two numbers has a huge impact on what the complexity is. And so what you want to do is instead of multiplying a bunch of enormous numbers times little numbers, make it so that you you do even more multiplies, but you do a kind of tree structure so that each multiply involves numbers that are about the same size. And in that way, you end up at the end just multiplying very few big numbers and a lot of really little numbers times each other, and it turns out to be dramatically faster. So if you want to compute this, you should instead say, oh, you can divide it up in various ways, but maybe you do all the even ones and all the odd ones, and you multiply those together. Something you have to think hard to figure out exactly what it is. So and then you go, oh, how do I do this one quickly? So you take half of them and you divide them up, and you do that product. And if you count it up, the total number of multiplies you do is bigger. It's more than n minus 1 multiplies. They're much, much better multiplies. And everything's very nicely balanced. And it turns out that is dramatically better speed-wise. And you can see this pretty easily if you try implementing both approaches. But if you try to compute this just by kind of going through one by one, I won't go all the way up to it, but like just up to 10,000, say. So s equals 1, s times equals I. So we'll just time this one thing. I hope this times the whole cell. That was pretty fast. That can't be right. Wait, what? Oh, look, guess what the first number is in a range? 0. So every time it's multiplying 0. That's pretty easy. Okay, so let me start a little smaller again. Okay. Oh wait, no, it's spinning here, so that means it's attempting to do the calculation. I think that I think I'm misinterpreting the time. I think it's timing that one line. So maybe I need 2% in the Sage cell server. Okay, well there's a command that, so instead of using this thing, we can do t equals wall time. That is the time that the clock says, and you can do wall time of t, and that will give you the elapsed time between those 2 points. So in this case, it was 2.27 seconds to do the factorial for 10 to the 5th. And if we do it here, the built-in version is hundreds of times faster. But I can implement the tree-like approach with exactly the same Python ints, the same numbers involved, using the prod command in Sage. So this just implements this generic tree approach. So if I do s equals prod of range 110 to the 5th, then it's doing exactly what I was just describing on the board over there. So let me make this all fit. It uses a whole bunch of different algorithms depending on the size of the numbers, and Karatsuba is one of them. For the really big numbers, it uses a fast Fourier transform. Let's see, why did it only print out one number? Because that's the way this works. Okay, so just multiplying one after the other, it takes 2.2 seconds, but doing the multiplication using the prod command, which builds a tree and multiplies things of roughly the same size, takes 23 seconds. Okay. Prod, by the way, is a function that's in Sage, which, again, Robert Bradshaw wrote in Cyclone, which is a generic command that takes as input a list and then multiplies the entries in the list together. But instead of multiplying it one after the other, it builds a tree structure and multiplies them that way. Okay, and yeah, if we did bigger numbers, the difference would just get more obvious. Basically, by multiplying one after the other, you don't get to take advantage of the use of the fast Fourier transform and Karatsuba and other asymptotically fast algorithms for doing multiplication of integers, which you do get to take advantage of when you're doing balanced multiplication. Yes, I think you do. Unless I'm completely confused, I think there's a lot of factors. Is that right?
You just change the order of multiplication.
I think there are actually more multiples. It's not very many yet. It's just that you have this. I haven't thought about this. Maybe I'm wrong. Yeah, there are actually not. How could it be more multiplies? There would only be more multiplies if the square was taken away. There's more memory allocation. Are there more multiplies than not? Maybe I'm just wrong.
If you print all the elements and add parentheses,
Yeah.
in this everything, right? It doesn't change the number.
Yeah, that's right. There's more of something. Maybe more memory allocation. Something that even more of it. I'm also being very big about the communication. You can go all the way down to individual numbers. Yeah. Yeah. Why is that? Because then there would be n minus 1 at the very bottom, and then working with that until you sort of actually. That is true. Right, because you're doing like, you multiply them all together to get a bunch of paths, and then find those. Maybe I should just write a little tree in one special case. 6 factorial. I can break it up. So 6 is. What? Yeah. So this is so. Yeah. So, all right. So I'll just put every time I do a multiply, I do a multiply to get this, and I did a multiply to get that, and then I had to multiply these two to get this one, and then I had to multiply these two to get this one, and then I multiply these two to get this one. So it's the same. There's a lot more numbers. A lot more memory allocations that happen. Yes?
Do you consider using binary?
Well, I mean, O then and what? So, if it's O then arithmetic operations, it's 1 times 2 times 3, that's O then.
Yeah, I mean, instead of using
But
genetic factorial
what, I mean, what matters is the number of bit operations.
Oh,
We're working with arbitrary large numbers. So the complexity really has to be in terms of that. And then the complexity of individual multiplies is a big deal. You're right. I'm certainly not going to depend on the multiplications of integers with. I think that there are a lot of allocations of but thank you for that. So, and by the way, a possible project, there's a huge amount of interesting stuff related to multiplying large integers. It's a very deep topic. We're multiplying small integers. There's a lot more than the algorithm that you use called the school book algorithm, where you just school person algorithm. So a possible project would be to describe one of the more interesting subtle algorithms for multiplying integers. All right, so that's way number 2. And way number 3 is cloud.sagemath.org, which is the thing that I made available like 2 days ago to anyone but me. And I will show you how that works. I made numerous improvements to it 3 hours ago, so hopefully that will be nice. So let me log out. So what I'll do is create an account, log in, and then do something, okay? So that will show you how this works. I have a terrifying message there. Everything is running in one single virtual machine on my desktop. The fact is my desktop is backed up, and when I significantly change this or make the website go away and be replaced by the actual release version, which will be running elsewhere, I'm not going to delete that virtual machine. It's still going to be sitting there. So I don't actually plan to delete anything. I just wanted to scare people off. And it's just a virtual machine on my desktop, but my desktop has 32 megs of RAM and 16 cores, so it's not completely useless as far as compute power goes. Okay, so you can create an account and just make up a name. So let's write William Math 480, and then an email address. That's probably already taken plus 10. If you want to make a bunch of accounts at a site, you can often do name plus and then anything you want at whatever, and they'll be treated as different email addresses by that site, but they're actually the same email address. The email address here is useful because I did implement password reset for this. So if you forget your password, you can reset it. So I'll make up some password and then agree to the. So here's the terms of usage I made up. I have a very, very long multi-page terms that the Center for Commercialization wants me to use, but I just kind of distilled it into a short version and a long version. But the long version is pretty short. The main point is to note that I'm not claiming to back up anything or making any other claims. Okay, then you click Create an Account, and now you have an account. And there's a settings page, which has a couple of settings. So you can change your email address, change your password, and the autosave interval, and so on, and some defaults. And then you can make a new project. So you might want to make one for this class, like that. And you can trivially at any time change the title and description of a project. So you can just put anything you want there. They are used in almost no way except to display it to you. So that's the only important way, and they're trivial to change. So don't worry too much about what you put there. Then you create the project. Here it is. When you click, you get this screen. There are a couple of things you can do. You can look at all of your files in that project. You can look at recently opened files. You can create a new file, worksheet, directory, or terminal. You can search through your files, and you can change settings for this project. You can also, each project is in fact a Unix account on a computer, and you can immediately run a command line command right there if you want to, like ls should output nothing, I guess. Print working directory, any standard bash command you can use here. So if you click here to create a new file, you get this screen. Here you can make various types of files. On Sunday last week, I started writing a new version of worksheets, which are pretty nice, but they're not done yet. That's what I've been using for lectures. That's what this gives you. I had an old version of worksheets, which is that little icon with parentheses, which you can drag and drop arbitrary files right here, which will then be files that get available. And you can also give a link to something on the web. What what we're going to do is make a terminal. I'll just call it term, and click terminal. When you do that, you get a command line prompt where you can type things. It looks like I should move my window a little to the right. Okay, and you can, right here you can click to make the font bigger. If you want that to be the default, you can click there. Copy works pretty good. Paste sometimes doesn't work right yet, so if you're having trouble pasting into the terminal, you can just paste into this box and it will get put into the terminal. But there are issues with paste due to how web browsers don't allow you access to the copy-paste buffer of the user for security reasons. Like what if you copied your password from somewhere to somewhere else, or some other private information, and any web page that happened to be running could, instantly get anything that you happen to have in your copy-paste buffer. Basically, that's off limits to web pages. And this terminal, though it looks like just something you type into, it's actually done with HTML, and it's like spans and divs and so on. So it's a little bit tricky. Basically, there's a hidden text area somewhere, and it might not be selected, in which case paste doesn't work. Okay, so now we have a command prompt, and now what I'm going to do is take the Math480 website and just type git clone and then paste it. So paste is in fact working fine here. And I type this. What this does is it takes all the files from the Math480 website, which is a Git repository. And remember, everybody here is going to make Git repositories in order to turn in your homework. And it clones them into your account in cloud.sagemath.org. And now from this point on, I'll just click on Files. And here it is. Let me make this bigger. So what I have is a directory. That's the one I just cloned. I can now click on this directory, and I get inside of it. And I can move to the parent directory. I can look at all the files that are there. In particular, let's look at the directory called, lectures. And here you have the lectures. So I can click on these files to open the worksheets. And you also have things like lecture 6 example, which is an example of a Python file that I made, which you can click on. When you click on a file, it opens an editor, which you can see here. And here it is. So this lets you edit code. You can click on the various files that you have opened. A terminal is just treated like a file like anything else. Like if you just close this or close your browser and then look later and click here, you get back to your same terminal session. Except I didn't ask it to save the font size as a default, so it shrunk again. And the session should still be running unless you, well, it just sort of stays running unless you exit it. So you can do things like start Sage here if you want. There are a bunch of programs installed, but you can start Sage. And then in this case, I can, for example, load the file f.pyx. Whoops, I'm in the wrong directory to load the file f.pyx. That's in this subdirectory. And this is just the standard bash prompt. You can do things like run vi if you know about vi. You can run Emacs if you know about Emacs. If you want, you don't have to. You have tab completion. You can run IPython as well if you want to try that out. And you have tab completion there. There's a lot of programs. Probably Octave is installed here if you want to use that, which is like MATLAB. Okay, so yeah, and oh yeah, of course, there's also all the worksheets. So if I go to lectures and then say lecture 6, then it brings up the worksheet that we were just looking at a minute ago. And here it is. And one nice thing is these worksheets are, they just sort of stay persistently running even if you exit the browser, but they're also synchronized. So if you open this worksheet on some other browser somewhere else at the same time and start typing, the changes are all immediately mirrored out. Also, if you do something like this, like you have the worksheet opened, and then let's say we make some change to it. So this is the version of everything on my laptop. And let's say, let's see, what should I change? Well, I'll just put note, this doesn't work well. Oh. The cursor jumps the first time it synchronizes. Sometimes I need to fix that, so watch out for that. Turns out when you're synchronizing, when you're doing editing of one document on multiple computers, one of the hardest things involved in synchronizing is keeping the cursor in the right place. you wouldn't even think that would be a major issue. But a lot of the merging stuff is easier than just dealing with the cursor. This doesn't work well. Okay, so save that. So what saving does, as you type, everything is sent back to the server and stored instantly, but it's not stored on disk. When you say save, it takes the worksheet and writes it out to the disk. So at this point, if I were to look at the actual file, which I'll do using the terminal, then I'll see that that line has changed. What has happened? Your startup disk is full. That's not good. So let's see. One other issue is with the terminals is sometimes you have to close and open them. The reason is that if your internet connection breaks completely, then the web browser will reconnect to the website, and it gets a different ID when it connects, and the web server doesn't know that the terminal is associated with that particular user, and so it has to, you just have to open and close it. The terminal itself will be exactly like you left it, so you don't lose anything. It's just that I have to implement some extra code for that to work. In any case, if we look at the worksheet that I just modified under Lecture 6, then you'll see that doesn't, let's see. So right here it says, doesn't work well. So I've made that one change. I guess I'm also giving you a tour of how to use Git while I'm at it. So what I'm going to do is say git diff. This is a Git repository. It shows me the changes I've made, which is that one line has been changed. And now I can do git commit -a-v. And what that will do is allow me to check in my one change. I noted an issue. And then I can do git push. And now the change gets pushed out to GitHub at this point. Like if I were to now look at GitHub, I would see that the worksheet has changed and that there was a recent commit. So note that in GitHub, I made that change. Okay. Now if I go to my account that I just created, my Math 480 user, which is on, so everything I just did was on my laptop, by the way, even though the website looks the same. It's a local version running on my laptop. Notice that here it's, it's as it was before, but I can now go to the terminal and do git pull. I think I should get some sort of conflict because I think I've probably made some changes, but I'll show you how to deal with that. So what git pull will do is it'll say, if you haven't changed anything locally, actually even if you have, what you'll do is it'll try to take all the changes from the website and merge them into what you have locally. So just to make sure that there's some issues and that this is difficult, let me make a change to sort of my version. So tour of 3, let's say. So I'm making a change here. So what this will do is it'll give me an error, actually, because I have an unsaved local change. So I'll try it, and I should get an error when I do git pull. Okay, I guess I didn't get an error. I think the mistake I made, sorry. The mistake I made was I didn't save this before doing that change. And so what happened was I just, let's see what happened exactly. Oh, okay. So what happened was I didn't save anything. So what happened was that it, okay. In any case, the point should be that that you can sit here and make all kinds of changes, play around with the code that's associated with the lectures, but at the same time you can pull in new things from the website, from GitHub. So if you log out, you log back in later, you could just do git pull, and you can get the new version of all the code that's relevant to this class. It's nice to be able to have. I guess it's not so interesting because there isn't much new that I just added. All right, so back to this lecture. So you've now seen 3 ways to use Sage here, and or to use Cython really. Actually, I haven't shown you Cython in here, so let me show you that really quickly. So in order to write Cython code in here, what you do is you write %Cython at the beginning of a cell, and then the rest of the cell is Cython code. So it's pretty straightforward. Let's take a function like we had before, where I'll declare a data type so you know that it's Cython, and then return n times n. And what you do is hit Shift-Enter, it then evaluates that code, and yep, there it is. It gives you a link to, this link looks pretty ugly right now. It gives you a link to a file that will show you the auto-generated C code and let you nicely browse how it corresponds to this Cython code. Here it is. Whoops. Okay, well I guess that's not working. Maybe I have to click here. Nope. All right, well I literally wrote this a few minutes before class, so maybe not surprised it isn't working. Let's see if evaluation works. Yeah, so at least you can run the code. Okay, so that's one way to write Cython code. There's actually there's a ton that's involved depending on the context in writing Cython code. So there are a ton of different things that can be involved. So for example, you can write your own standalone Python projects that involve Cython code. In that case, you can write perhaps a bunch of Python scripts and then some code that's in the Cython language, which is very similar to Python but compiled. And then in a setup py file, you would describe extra information about how that code gets compiled. When you do it in the context of Sage, there's in the notebook, there's just doing %Cython, but then there's also how you add Cython files to the Sage library. It's all sort of complicated in different ways. In any case, we're basically out of time. The next thing that I'll tell you right at the beginning of Monday is a very brief history of why Cython was a major reason for choosing Python as the language for Sage and how important that is to writing mathematical software. And then I'll give you a tutorial about how to actually use Cython to do things. So I'll show you how Cython differs from Python and what sort of amazing things it gives you. In particular, you can get speedups of a factor of 100 for certain types of operations. It's really the only reason that Python is a viable option for doing mathematical or numerical work, in my opinion. Why did that not work? Yeah. What?
I'm Abe. So it's the one.
Okay, cool. Yep.
So, question regarding homework 2.
Sure.
Is it okay to have a dependency on matplotlib?
Yes, that's fine.
Okay,
Yeah, thanks. Yeah, that's perfectly okay.
I'm thinking of doing